In this video, we're going to be doing a practice for an FRQ of rotations in AP Physics 1. So, on this problem, we have a frictionless surface except for the region between C and D. The plunger is going to be returned to its original position and both blocks are removed. A solid uniform sphere is placed at point P as shown. The sphere is pushed by the plunger from point A to point P with a constant horizontal force that is directed toward the sphere's center of mass. The sphere loses contact with the plunger at point B and continues moving across the horizontal surface toward point E. In which intervals, if any, does the sphere's angular momentum about its center of mass change? Check all that apply. So, what we know is we have the force of the plunger, which is horizontal and applied through the center of mass. So this is our sphere. The plunger is pushing it here, and that is going to be at its center of mass. We have normal force acting upward. We also have the weight, mg, acting down, which is equal to the upward force. It's our center of mass. And force applied. And we know that our torque is going to be about the center of mass. And we can analyze this torque about center of mass. So we can analyze what our forces are for, our torque is for each of these forces. So the weight is going to be at or through the center of mass. Therefore, it's going to be no torque. Now, our force of our plunger is going to be through our center of mass. Therefore, there is no torque produced by this either. Now, we know that Fn is vertical, though. So that means we're not really considering this. And right now, and we know the position vector from the center of mass to the contact point is vertical. So that means we can represent that as our lever arm R is going to be parallel to our force. And that means that our torque is going to equal to RF sine of theta. When two forces are parallel to each other, that means that they're directly on top of each other, basically. Or you can write that as like just one line, right? And then that's going to be 180 degrees. So sine of 180 degrees, RF sine 180 degrees on the unit circle. At an angle of 180 degrees, your height is 0. So that is equal to 0. Therefore, torque is equal to 0. So that means that now that we've analyzed all the torques about this center of mass where all the forces are being applied, we can conclude that there is no external torque about the center of mass. And what that means is that you can conclude that angular momentum does not change. So it's going to be conserved because they all cancel out or are equal to 0. So now we can analyze what is going on in each interval. So that was for interval A to B. Let's move this. So this is from A to B. So from A to B, no external momentum. So that's not going to be checked. Now from B to C, on this interval, we are still going to have friction there's still going to be no friction. So it's going to be frictionless. So now what we have is no plunger force. So it's after it was the object was acted on by the force of the plunger. We still know that it's going to be a frictionless surface. Frictionless surface. And the forces we have are still going to be our weight force through our center of mass. So our diagram again is we still have our weight and we still have our Fn vertical, which is up. Again, what we have is that our weight, that's going to produce no torque because it is directly at the center of mass, and R is going to equal to 0. And again, the normal force is going to be vertical and is also aligned with the radius. That means that you have no torque. So again, we have that there is no change in angular momentum. No change in angular momentum, which we can just right here. So both of these, there is no change in angular momentum. Now we can consider the region from C to D. This is going to be our only interval with friction. So there is friction here from C to D. So now that we have friction, our forces are going to include additional friction. We have friction, we have weight, and we have Fn, horizontal. So our diagram again, we're going to have our Fn. Downward, we're going to have, from our center of mass, we're going to have our weight. And now, we're opposite to our motion is going to be is in this direction, so our friction is going to be in this direction. So we know that friction, it acts at a contact point of the object. So we know that torque is equal to R times F, sine of the angle in between. So here we know that R is equal to the radius, which we represent as big R. We also know that our friction is going to be horizontal. And we also know that our position vector from our center of mass to our contact point is vertical. So that means that our force, the position vector from the center of mass to the contact point, is going to be upwards, right? And then we know that F, our friction force, is going to be down. So that is going to be an angle of 90 degrees. So that means when we plug that in, we're going to have 90 there. We're going to have torque is equal to RF sine 90. So that means that our torque is going to be R times F. And this does not equal to 0. That means that angular momentum here does change. So we can actually check this off. Now let's go back to analyzing another frictionless surface. That's going to be from D to E, our final interval. This is going to be frictionless, and there's still, we're going to have our only forces are going to be weight and the normal force. And both of those, they contribute 0 torque. So that means angular momentum from D to E, angular momentum does not change because there are no net external forces acting on the object. So again, we have that our forces were weight and Fn, and these equal 0 torque. So overall, we have that the sphere's angular momentum It only changes when you have, okay, spheres, angular momentum only changes when net external forces act about the center of mass. We know that from A to C, from D to E, all forces, they either act through the center of mass or they produce no torque. And for those reasons, angular momentum does not change. Now, from C to D, we have that friction is going to act at the contact point. And that makes R not equal to 0 because there's going to be a distance from that. So then because R does not equal to 0, that means that torque is not going to equal to 0. Therefore, we have that the change in angular momentum is not going to equal to 0. So an angular momentum change does exist, and it's only going to be in this interval from C to D. Now, what we can do here is we can actually analyze the sphere and the angular momentum a bit more. So we know that for a sphere, which we had in this case, if it's a uniform solid sphere, we know that the inertia of the center of mass is 2/5 mass times the radius squared. And the rolling without slipping condition is V is equal to omega times R. K translational is equal to 1/2 mv squared. K rotational is equal to 1/2 I omega squared. So our I, we know, is 2/5 mr squared times omega squared. And we can see that 2 cancels out. So you're left with 1/5 mr squared omega squared. So now we can actually change this to solve for omega. Omega is equal to the velocity divided by the radius. So subbing that in here, we're going to have 1/5 mr squared times v squared over r squared, because we just have to square this term. That's going to simplify to canceling out that r squared here, 1/5 mv squared. Now, if we want to solve for our total kinetic energy in this setup, we have K translational plus K rotational, because our ball, our sphere, it had to roll in this scenario. Because it had to roll. Oh, and by the way, this bottom question does not include this top question. Let me actually fix this problem. So during this was the only part where we had mu. So going back to solving for our total, our K translational energy was 1/2 mv squared, and our rotational was 1/5 mv squared. We need to get a common denominator, so you have 5/10 mv squared plus 2/10 mv squared, and your total kinetic energy is 7/10 mv squared for a solid sphere. Now let's do our rolling cylinder problem. This is going to be a rolling cylinder. So for the rolling cylinder, we want to draw the FBD. But let's first read this question. A cylinder of mass MO is placed at the top of an incline of length M initial and L initial, and height H initial, as shown above, and released from rest. The cylinder rolls without slipping down the incline and then continues rolling along a horizontal surface. On the grid below, sketch a graph that represents the total kinetic energy of the cylinder as a function of the distance traveled by the cylinder as it rolls down the incline and continues to roll across the horizontal surface. So, let's draw this FBD. It's on an incline and our object is like this. So, on this object, from the center of mass, we're going to have the mass times the gravity acting down. And then for the object, it has an Fn that is acting at the point of contact. The point of contact. So it's actually like, it is in contact like right here. But I want to like, this is like a better representation, so mg. So you also have the static friction Fs, because right now it's at the top. So this is FBD at the top. So when it's at the top, that means that there's friction that is keeping it from sliding down. And because the object is not in motion yet, that means that the static friction is going to exist and it's not going to be kinetic friction yet. So then let's resolve some of the forces that are along the incline. Now on the incline, the component of gravity at mg is equal to Fg, and it's also equal to the weight. So our component of the gravity that is going to be parallel to the incline is basically this thing. It's like basically any of these. So we can draw a triangle here. This FGX, that is, or FG, that's parallel to the incline, F parallel, we can just write weight parallel. That's going to equal to mg sine theta. So now if we apply Newton's law, summation of forces in the x direction is equal to 0 because they cancel out. We can also define our coordinate system like this, and that's going to be mg sine theta. Sine theta is going to be pushing down the incline, and we're going to define that as positive. And then we're going to subtract FFS because it's acting in the negative direction. That's going to equal to the mass times the acceleration. Summation of F is equal to ma. And, or actually, yeah, let's just write that there. We're going to make this our first equation. Now, after this, we want to describe the torque about our center of mass. So our only force producing torque is going to be friction. Only friction produces torque. So what that means is that you can set torque equal to the Fs, your static friction force, times R. That's because torque is equal to Fr sine of theta. So the force is Fs, R is going to be the radius, that's the distance from the lever arm, and then your angle in between them, you're going to have, so imagine this is your center of mass, and then this is the circle, right? So just imagine that it's like this way. What you have at any point of contact, that's your Fs, and it's going to be pushing that way. And then this angle in between the two forces, this is going to be your lever arm R. The angle in between that is 90 degrees. And sine of 90 degrees on your unit circle, that is when you have 90 degrees, that's going to be equal to 1. So that means that it's just going to be equal to torque times F SR. So now we know that, again, for a solid cylinder, I of a I at the center of mass for a solid cylinder is going to equal to 1/2 mr squared. So because of that, we can actually substitute that in here. So we have FSR. Oh, we also have that. Let's first declare that torque is equal to I times A. So we can write IA here, or just IA, or alpha. So this is going to be, and we can also divide by OR. So we have torque equals to FSR. So we have FSR is equal to 1/2 mr alpha here times R. And we also have our rolling condition. Our rolling condition is A is equal to alpha times R. Alpha is equal to A over R. So our Fs is equal to 1/2 mr A over R. So we can see here that our R, it cancels out. Because it cancels out, we're just left with Fs is equal to 1/2 ma, and that's going to be our second equation. Up here we have FSR, torque is equal to FSR, Fs, solid cylinder, we have 1/2 mr squared times R. So yeah, you just divide by Fs. So here you have alpha A over R. Yeah, so then your R is over there, and you actually can, you can divide by R. So now your second equation, we can solve for acceleration with our equation 1 and 2. So we can sub 2 into equation 1. That's going to be mg sine of theta is minus 1/2 ma is equal to mass times acceleration. So mg sine of theta is equal to 3 over 2 mass times acceleration. And after this, we can multiply by 2 over 3 and 2 over 3 here. And we can also divide both sides by our m. And we just are left with A is equal to 2 over 3g sine of the angle theta. Now, also, we know we can solve for the translational and the rotational kinetic energy for the cylinder. Kinetic energy and our rotational kinetic energy. For a solid cylinder, again, we have our 1/2 mr squared. Translational is 1/2 mv squared. Our rotational is 1/2 I omega squared. So that is 1/2 mr squared omega squared, which is 1 over 4 mr squared omega squared. Now you can substitute in omega equals to v over r. So k rotational is going to equal to 1 over 4 mr squared v squared over r squared. I'll highlight where I just substituted those in. Omega here, and up here are 1/2 mr squared right there. Now after this, we can find our total kinetic energy, which is 1/2 mv squared, which is, this is k trans plus k rotational plus 1 over 4 mv squared, which is 3 over 4 mv squared. And we know that this means that for a rolling cylinder, our K rotational is always going to equal to 1/2 of our K translational here, if we take the ratio of the two. So that means that the graph is linear on an incline. The reason for this is because that the work done by gravity can be represented as work equals to force times d. So that's equal, our force is mg sine theta. That's the component of gravity, and that's times x. That means that k is equal to mg sine theta x, and that is going to be linear in distance. Now we can move on to our next question. But we can also, we solved these two questions using rotations, but we can also solve the rotational physics. We can also solve them using energy, work energy. So for the first part, for our first FRQ, by doing this with energy, so this is method rotational. This is for our method of using energy. So if we want the speed at the bottom for the uniform, I'll write this over here. For us to derive the speed at the bottom of the hill of the cylinder, we have a uniform solid sphere again, right? And we know that it rolls without slipping. And we know that it was released from the height of h initial. And we were not mentioned a friction. We're not going to mention the friction here. So let's see how we represent this. So our initial energy at the top is equal to mgh initial, and our final energy is equal to k trans plus k rotational. So that means that you can, and we also know that for a solid sphere, I is equal to 2 over 5 mr squared, and we have our rolling condition for a sphere. V is equal to omega times r. So for our total kinetic energy, we have 1/2 mv squared. For our rotational kinetic energy, we have 1/2 I omega squared. So k rotational is 1 over 2 over 5 mr squared omega squared. That's 1 over 5 mr squared omega squared. And omega is equal to v over r. So this is equal to 1 over 5 mv squared. So k total is, that's k trans I meant to write. K total is 1/2 mv squared plus 1 over 5 mv squared, which is 7 over 10 mv squared. So now we can solve for speed using energy instead, which is mgh initial is equal to 7 over 10 mv squared. Now we can actually cancel the m's because it's on both sides, dividing by m. So gh initial is equal to 7 over 10 v squared. Now, after this, we just have v squared by multiplying both sides by 10 over 7. Now, v squared is equal to 10 over 7 g times h initial. Now, if you take the square root of both sides, you know that v is equal to the root of 10 over 7 g h initial. Now, for the acceleration of the sphere, we're going to have from the rotational derivation, which you should have, which we did earlier, a is equal to g sine of theta divided by 1 plus I over mr squared. Here we know that this is equal to 2 over 5. So we know that a is equal to g sine theta 1 plus 2 over 5. 1 plus 2 over 5, you can also write that as 5 over 5 plus 2 over 5 by using some fraction math. You have g sine theta over 7 over 5. When you have a fraction in your denominator, you can actually flip the numerator and denominator. So that's going to be 5 over 7 g sine of theta. This is for our first FRQ. Can we make some room? Now for a second FRQ by using an energy approach. So this is a method of energy. Energy. And this is a method of using rotation for energy. So what we know is that the speed at the bottom is going to have a moment of inertia of 1/2 mr squared. So for our k total, we're going to split this into k trans plus k rotational. That's equal to 1/2 times 1/2 mr squared times omega squared. That's 1 over 4 mr squared, omega squared. Omega is equal to v over r. So k rotational is equal to 1 over 4 mv squared. Now, if you just add those, k total is 1/2 mv squared plus 1 over 4 mv squared, because it's equal to translational plus rotational. Now, if we solve for speed, we know mgh initial, large H initial, is equal to 3 over 4 mv squared. This comes from knowing that our UG is equal to our kinetic energy total. This is because there's energy conservation. So we have v squared is equal to 4 over 3 gh initial. The reason for that is 4 over 3, that cancels out there. Now we want to take the root of both sides. So v is equal to the root of 4 over 3 gh initial. After this, we want to find the acceleration of the cylinder. So by using the same formula that we derived earlier, A is equal to G sine theta over 1 plus I over mr squared. Here we know that I over mr squared, that's going to equal to 1/2. You're going to have G sine of theta divided by 1 plus 1/2. That's going to equal to G sine of theta divided by 3 over 2. Now, you're going to flip the fraction, so that's going to be 2 over 3 G sine of theta. So that means that if we compare these two, we have that the acceleration of the sphere was equal to 5 over 7 G sine of theta, and we have the acceleration of the cylinder is equal to 2 over 3 G sine theta. The only difference in these two is the fraction that is right here. So in order to compare which one is larger, let's compare the fractions. 5 over 7 and 2 over 3. So we know that 5 times 3 is 15 and 7 times 2 is 14. Therefore, we know that 5 over 7 is going to be greater because you can just do the cross multiplication to check which one's larger. But also we know 5 over 7 is 0.714, and we know that 2 over 3 is 0.667, so that you know that A of the sphere is going to be greater than the acceleration of the cylinder.